Okay, last session we discussed about introduction into process management. We were learning about what is process and how it is, uh, what is the importance in an operating system. Can you hear me? Can you hear my voice? First of all, let me know that, then I can proceed. Okay. Right. So we learned that process is a program in action. It's a program in action. And when you take a program, there are many processes. That's what we learned in the last session. And we can divide processes into two types. One is mainly input-output bound processes, which means processes that are created or triggered from external to the system. Processor-bound processes means processes that are triggered within the system without any user interaction, right? So we discussed about that. What are the reasons why a process is being created? Mainly for a new batch. It could be a completely new batch job, or it could be a program that is started by a user, or the operating system wants to do something, or it may be already a running program that is already a running program trying to trigger or start another process. So these are some reasons why a process should be created. Right. And also, when does a process terminate? There should be reasons. One is after its work is completed, it could be a normal termination, and or it could be the time has been exceeded. So each process will get a particular share of time when it's trying to use the CPU. So if it's something taking abnormally, the operating system can decide to terminate. So the time, execution time matters. Or maybe the process was requesting a resource and it is not available. Or it could be an execution error, or there could be a memory access violation, uh, or maybe operating system or the parent process was asking the process to terminate. It could be a request coming from that, or altogether when the parent process terminates, all the child processes also get terminated. When we discuss what is interrupt, interrupt is an event that changes the sequence of execution of a process. When a process is running, interrupt is some kind of an event that can change the state of the process. So it could change the sequence of execution. Whatever is happening normally, interrupt can go and change it. It's like a disturbance. So this interrupt is normally triggered through external bound processes or external events, mostly, especially with the keyboard events, or could be mouse events, any kind of events that can come externally or internally that changes the process, that is called interrupt. So that's what we discussed in the last class. Okay, today very important thing, very small but also very important stuff, because when it comes to past papers, part 1, part 2, you definitely will have something coming around this concept called process states. Okay. So in a computer process, in a computer system, or let's say in an operating system, you have many processes running. So if you take a process will have mainly a state, and it can also have transitions. It could transition. So state means what is the current position of the process. So it indicates the execution state of the process. Basically, when a process is there, with the state, we can identify in which position the process is. So if you can see here, for example, this green color circled circle thing here, this ready, running, blocked. So these are called states. A process could be in ready state, it could be in running, blocked. There are a few more other states as well, but this just to get an idea, this is what is a state called. Process transition means when a process is changing states, there will be some kind of a event or some activity that is making the process change its states. That is called process transition. So this represents the changes between the process states. You can see here, those are indicated with the arrow marks. Creation. So when it's coming to ready, it is coming from another state here. So that action is creation. Here from ready to running, you have to dispatch a process. And when it is running, sometimes if it is taking more than what is needed, it could either terminate or sometimes it comes back to ready state. So if you take any single process, a process may be in any of these states. And when it is trying to change its states, it will go through a process transition. So that's the idea behind these two. Very simple. Right. Now, generally, there is a standard diagram which people state, which people talk about when it comes to processes. So if you take any process, it will first begin with this new state. We call this new or create state. Once you have created, it will change into the ready state. Just when it is ready to execute, it will come to the ready state. Then from the ready state, if it's based on the priority, if that process is the next one. So basically the ready state is, if a process is coming to the ready state, that means that is the process that is going to be running next. So from there, once the CPU is free, it will dispatch itself and move into the running state. Once it has completed the normal execution, it will terminate. Exit means terminate. So it will release itself from the CPU and goes to termination. This is the normal procedure. So process will begin with a new state. It will admit itself to the ready state, which means it is just ready to get executed. Once the CPU is free, it will dispatch itself to make this process running. So when you say it's running, it is already using the memory and the CPU. Then once the normal execution is over, it gets exit. So that's the normal part. Now, once it is running, there can be a process that is taking more than the intended time. In that time, because there are other processes also waiting somewhere in the queue, it is waiting. So if this running process is taking more than what is needed, what happens is there will be a timeout event which will change the state from running to ready. Okay, keep in mind, clearly listen to this flow. So normal path I explained first. Now I'm coming back to explain the remaining states. So now let's say the current process is running and it is taking more time than needed. So there will be a timeout event and it will switch back to ready state. Then from ready state, once it has come to ready state, now there is something called a process scheduler. Uh, so there are three types of schedulers. I'm just generalizing the name here. The process scheduler will now look and see the priorities of this current one which came as timeout, as well as all the other processes that are ready to be executed. So it will look at the priorities again based on some algorithm. It will check which process should be going back to running again. So based on now this guy has come back, so maybe the next available process which was in the ready state will go back to running. So until that, this guy has to be somewhere. No, the currently running process has to be somewhere. So what will happen is it may put it into the ready suspend. Uh, if there is no memory to hold it, it will send it to the secondary storage here. So these two processes I'll just mention. This ready suspend, block suspend, both are in the secondary storage. Mostly that information will be there. So if it is not, if there is, if there is not much enough RAM to hold the older process, it will switch it back to ready suspend, which is in the secondary storage. Right. So that was one flow I explained. Now, sometimes when you are running, when the process is currently running, not because of timeout, there could be maybe another event, another interrupt happening. As I told, interrupts are mostly if it's a keyboard event or if it's a mouse event, mouse click event, the currently running process might get affected by that event. So during that time, it will not go to the ready state, it will come to a blocked state. So here timeout is timeout. I explained, because it's taking more than what is needed, the time more than what is needed. So it timeouts and comes here. But this part means because of some input output operation from the running state, it will come to block state. Once it is blocked, again, this is in the virtual memory on the RAM area, or maybe temporarily it is hold, and it will wait until the current input output operation has finished its work with the CPU. Then it will, from the block state, it will quickly switch to the next readily available state. Then again, the normal flow will work. In this case, if still there is no memory, just like in the ready state, when this is timeout and coming here, here also when the input output happen comes and it changes to block, and there is no space in the virtual memory, then it will suspend itself and go back to the block state. Once, so block suspend. So basically this is blocked. This is called block suspend. So there is also another name for this, swap out. Swap out. So it will learn that in the next couple of slides. So for the moment, it changes into the suspend block state or block suspend state. So here also these, as I told you, just like here, this is like in a secondary storage. Then after sometimes, if it wants to come back again, either the blocked one will go and activate itself and come to block state, then come to ready state again, which will normally do the work. Or if there is no immediate availability to activate itself, if it's taking more time again, then it will trigger an event and go to the ready suspend state, which means mostly this ready suspend is like the uh, it is a state where you have more processes in a queue. So basically this is like in the queue kind of state, which is making sure that this is not in a block state, but it is ready to execute based on the priority list. The next available, so this will get a number. Basically, this is all related to a single process now. So each process, when it comes to a ready suspend state, it will get a priority order or priority number order. And once the CPU is ready, once the CPU is free, the next available thing will come to ready state and then go in the normal flow. So this is what is called 7-state process transition diagram. So one thing you have to remember, we'll be learning now in a couple of minutes all the explanations. One thing you need to know is you should be able to memorize this diagram. In this case, all these 7 states plus from which state to which state the arrows are going and what are the events happening with that. So that is what they expect in the most of the questions, even MCQ and all, there are questions now, even in MCQ, even in part 2, you get couple of circles like this, and maybe 1 or 2 hints will be given. You have to fill the remaining, like fill in the blanks, right? So if you knew the normal flow of events, or the whole idea from where it is starting, from where to where you have the arrow mark going, if you have that idea, you can easily do this. One key point I would like to uh, highlight, very easy to remember, is if you look at this area, there is a similarity to memorize, right? Uh, that is, you can see once something is coming from running to ready, or uh, running to ready state, or running to block state. You can see these arrow marks are almost having the similar transitions. See, from block to ready, you have to have an event occurring. From block suspend to ready suspend, you have to have an event occurring. At the same time, if you want to take something from this queue to the ready state, you have to activate it. Otherwise, if it's you suspend it and bring it back to the queue. Here also, block suspend. If the virtual memory is available, it will activate itself. If it is not available, waiting for a long time, it will suspend and come here. Then from here, it will trigger an event, and if it is ready, it will go there. Here also same thing. If the blocked one virtual memory is also available, and there is priority is also there, it will go to the ready state. So this is what uh, the state diagram is. And the other thing is these two, or maybe I can even include this one as well. These are all from the secondary storage part, mainly these two, so ready suspend and block suspend. They are from the secondary storage. These three are the dynamic ones, which are using the primary memory, the RAM, ready, running, and blocked. So when the process is in these three states, they are using the main memory. So there are some MCQ questions asking those kind of details as well. Right. Okay. Are we clear with that basic introduction? Now a little bit into the explanations. So these process transitions, which we discussed earlier, these arrow marks. The operating system's role is to manage the execution of existing and newly created processes by moving them between the two states until they finish. For simplicity, modern operating systems support the idle process, which is always ready to run, and never terminates. That means uh, now modern operating systems, we always tell that the CPU is running only a single process at a time. So with that concept, which means a process is when you have a process that is always ready to run. There is no concept of, very rarely there is a concept of a termination. So termination happens only once that process is over. So it will basically change its state to uh, terminated or something like that. So newly created processes are created and marked as ready and are queued to run. As the single running process terminates or is interrupted, it is marked as ready by the operating system. Sorry, it's not. It's marked as ready by the operating system, and the next ready process is commenced. No. This should be, I think there's a correction here. This should be marked as terminated or blocked. That's the correct term for that. Then only it makes sense. Otherwise, it's a problem. So if a single process terminates or is interrupted, it is marked as terminated or blocked by the operating system, and the next ready process is commenced. So there will be another process which is marked as ready now, that will start, right? As I explained in this diagram. Okay, basically here, this is running. The current process is running because of some event or maybe timeout. This will go to ready or this will go to blocked, and the next ready state process will start running. Whenever the next, so basically that process will come from here, from the second process. Let's imagine P1, P2 is there. P1 is running. Now P2 is the next available process, means the while P1 is running, P2 will be in the ready suspend state with the priority number. Like that, P3, P4, P5, P6, up to how many processes that are available. Each one will be either in the ready suspend state, but they will have a priority number. So once the current one, P1 is running and it has exited or terminated, or maybe it has come to block, the next available priority process will come to the ready state. So that's what this point is telling here, the last point. As the single running process terminates or is interrupted, it is marked as terminated or blocked, depending on the scenario, by the operating system, and the next ready process is commenced. Here, the operating system has the role of a dispatcher, dispatching work for the processor according to some defined policy addressing. So there will be a question. Basically, how does the operating system decide who should use the CPU next? I just mentioned a imaginary thing called there could be a order. There could be a what do you say? Some kind of a priority identification might be given, marked with each process who should go next. So how is that decided? So operating system will decide based on the fairness, based on the priority, or maybe apparent interactivity, which process needs interactions, those kind of things. So basically operating system will decide that policy and prioritize that list. Since the process is brought to the main memory, it is put to running state and sent to the processor, or it is sent to virtual memory and waits. So wait means blocked. If the process is in the running state, upon its completion, it is removed from the main memory and transitioned to the terminated state, or it is suspended and sent to block state to the virtual memory. I think this is what I explained when the process is working. Right. So now we are going to discuss about each of these states, what is happening there, what are the importance in it. So you can see the same diagram I have shown here in the previous couple of slides. So the process starts with new or created state, and upon admission, it comes to ready state. From ready state, dispatch it itself and goes to running. And once it has completed normally, it goes to exit. So it releases itself, goes to exit. Similarly, if something is running, basically you start from here again. If it takes more than the needed time, the timeout, it comes back to ready state. And still, if you don't have memory to hold that previous running process, you can suspend itself and move it to the suspend ready state. And whenever it is ready, next time you will activate it and bring it back normally. So this is the one flow. The other flow is because of some event or interrupt, it can go to the block state. And if you don't have enough virtual memory to hold that process, it will suspend itself and go to suspended block. And maybe if there is again memory available, it will activate itself and come back to block state. And then from there, it could trigger an event and go back to the ready state and come to running again. Otherwise, if there is no space in the virtual memory further, and again, if it is ready to get executed, it will change itself to suspended ready. Then from there onwards, it will activate itself. So you can see these boundaries. Ready, running, and blocked is called the main memory because this is the active area. And these three states are in the secondary storage, basically like a base, database kind of a state. One other key point is any process that needs to run cannot come from any other processes except ready state. It has to come through the ready state. So even if it is a blocked one or suspended blocked one or suspended ready, all will have to come to the ready state. Through the ready state only, you can make it running. That's an important point, right? There is no transition directly to the running state except coming through the ready state. Right. Now we are going to discuss each of these states in a particular order. So first of all, the new state. In this step, the process is about to be created, but not yet created. Keep in mind, the process is about to be created, but not yet created. It is the program which is present in secondary memory that will be picked up by the OS to create the process. In this state, the process waits admission to the ready state. This admission is approved or delayed by the software called long-term scheduler. We'll be learning about schedulers, long-term, medium-term, short-term. So when a process is in the new state and waiting to go to ready, until that time, this long-term scheduler is holding that information. The operating system's role is to manage the execution of existing and newly created processes by moving them between the two states, either to the ready state or swept out and ready state. Swept out and ready state is this one, suspended ready, basically, right? So once something has come to ready state, operating system will be ready to transition between these two things. Either suspend and put it here, swept out and ready state, or it will activate itself and bring it back to the ready state. So that is something they are telling at this point. So the operating system role is to manage the execution of existing and newly created processes by moving them between the two states. So anything that is in this suspended ready state is already created, already new. It will not go back to new again. New happens only once, basically at the time of creation. It is just about to be created, but not created. That is what is called new state. So once it is there, it will either come to ready and do it. And if there is no, it's not ready, it will not go back to new again, but it will come to suspend ready. That's what is mentioned here. Okay. Second one, ready state. This is now something that is already created and ready to run. So after the creation of a process, the process enters the ready state. That is, the process is loaded into the main memory. You can see this boundary here. It is loaded into the main memory. The process here is ready to run and is waiting to get the CPU time for its execution. Processes that are ready for execution by the CPU are maintained in a queue for ready processes. This is an idle process which is always ready to run and never terminates. So once this is created, it is not terminated. So it is when you mark the process as ready, it is just waiting for the CPU so that it can do its running. Running state, this is the actual place where the process is executed. So the process is chosen by the CPU for execution, and the instructions within the process are executed by one of the available CPU cores. This state is called as active or execution state, which is executed in the CPU. So running means it's already active. So it's called active or execution. When in this state, if the process exceeds its allocated time period, It may be context switched and move back. Right. So if the process exceeds its allocated time period, it may be context switched and moved back to ready state or temporarily move to block state. I have also explained if there is a timeout happening, it will go back to ready state, or if there are some other events happening other than timeout, it will go to the block state. Right. So the running means something that is already active and executing. Block state. This is also known as wait. Whenever the process requests access to input output or needs input from the user or needs access to some critical region, the lock, which is already acquired. That means there might be some process already using some memory area, and this event or some external trigger is happening. Then what happens is the process from the running, it will come to the block state or wait state. There is another one called sleeping state as well, right? So the process continues to wait in the main memory and does not require CPU, right? So at this point, it will still reside in the main memory. Maybe at this point, we can say it's also trying to use the virtual memory. So virtual memory is a buffer. No, we have learned virtual memory is like a supportive memory for the main memory. If the main memory is almost full, so it will wait in a main memory. Once the input output operation is completed, so the process goes to the ready state. Now it was in block now. If it wants to run again, it will first change to ready state and quickly it will dispatch and go to the running state. It will happen very quickly. So that's what is explained here. So why it came to blocked? Because of some event, because of a user event or some kind of a input output need, or maybe there was some other process trying to access the memory or CPU. So it will change itself to the blocked, and the current the CPU will be now be used by the input output process. Once that input output event is over, it will change itself to the ready state. So which means once the resources are obtained, the block process moves to ready state and then to running state. It's very simple to understand. Exit is very simple. Process is killed as well as the process control block is deleted. We'll be learning what is a PCB in a couple of slides. So PCB is basically some kind of information each process will contain. In a process control block, it has information about the current running process. So once a process comes to exit state, it is deleted. Normally, these processes are removed from the main memory, and the processes which were not removed are called zombies, right? So this is the general thing. Once something is running and completed, it will change to exit, and normally it should come out of this main memory area because now other processes are going to use it now. But there could be some processes, even though its work is over, it will be still residing in the main memory, right? Those processes are called zombies. I believe you know what the meaning of zombies are. If you might have seen some horror films, zombies are people like they are dead people, but they still have life. They come like, you know, scaring people. You might have seen in some films. Zombies. If you search on the internet, you will get uh, thousands of images from films. Uh, so that is called. This is what happens in the terminated, right? So mostly these virus programs and all, they create a lot of zombie processes. Why? When it creates zombie process, what happens is your memory is loaded, but they are useless. All those processes are useless, not doing any benefit to you, but just occupying your memory, right? So that's terminate. Next one is the suspend ready, or we call it swept out and waiting. Swept out means mainly you're sweeping it out, you're sweeping the process out of memory and making it wait. That's why it's called swept out and waiting. So you can see this boundary here from ready to, so from this main memory, it is coming to this region, secondary memory area. So process that was initially in the ready state but was swept out of main memory and placed onto external storage by the scheduler are said to be in suspend ready state. If a process is in ready state for a longer time, that proves that process moves to the virtual memory in order to provide space for other high priority processes. The process will transition back to ready state whenever the process is again brought onto the main memory. So as I explained earlier, so the process might be in the ready state, and now there are, so let's say it is now here in the ready state, it is waiting for a long time. So in that case, it will put back, it will transition itself to the suspended ready and give space to the other processes to be in the ready state and then start the execution. Once the CPU is available, it will again activate itself or admit itself into the ready state. That's what is the third point. The process will transition back to the ready state whenever the process is again brought onto the main memory. The other one, last one, suspended blocked. Suspended blocked. There are different names for this. Suspend, wait, suspend, blocked, or swept out and blocked. Similar to the suspend ready, but uses the process which was performing input-output operation, and lack of main memory caused them to move to secondary memory. So there is no space in the main memory. That's why it came back to this one. If the main memory is too loaded or to give space to high priority processes, the processes with block state in main memory are moved to virtual memory as swept out and block state. It will come here. The state of this process needs to be resumed when the main memory is okay. When there is space, it should go back. So it will either go back this way or it may go back to, it will come to the suspend ready. When work is finished, it may go to suspend ready. This place, and from here, it will go to the ready state. So two ways it can happen. If main memory is available, from suspend blocked, it will go to block state again, activating itself. Otherwise, if the main memory is not available and this is waiting in a long time in suspended block, it will transition itself to the suspend ready state, and then from there it will go to the ready state. Right. So this is what is a process control block. Each process will have process ID, state, pointer, priority, program counter. These information will be there. So process control block is a data structure maintained by the operating system for every process. The PCB is identified by the integer process ID, PID. PCB keeps all the information needed to keep track of a process as shown in this table. So if you look at the explanations of these things, there could be many other information as well, but generally these are some information that may be in a process PCB. So it will have a process state, which indicates what is the state of the current process. It will have a process ID, which is a unique identification for each of the process. It will have program counter. We have learned this. Program counter is a pointer to the address of the next instruction to be executed for this process, right? So each process will have set of instructions. So this process will have information of what is the next thing to fetch in the memory, the address. So program counter will have the address. We have learned that it is an address register. And it will have CPU registers, various CPU registers where the process need to be stored for execution for running state, which place we have to store the current process when it is in the ready state. And memory management information. This includes the information of page table, memory limits, segmentable depending on memory used by the operating system, and also input-output status information that is allocated to this process. So a lot of information is stored in a single process control block. So any number of processes, any of the processes in the operating system, each and every of this process will have its own PCB. This PCB can vary operating system to operating system, right? In Windows, if you take a single process, it may have a certain structure for the PCB. If you look at Linux, it will have a different PCB, right? So that's what they say. That means different OS contains different information on the PCB. Throughout the process lifetime, PCB is available. When the process terminates, PCB information is also removed from the memory and no more needed. Obviously, we don't have to store that information. Right. One last point for today. Input-output models. Generally, when you have an input-output event, that event is much more slower than what is happening within the CPU. That is, we learned last class, there are two types of process that happens: input-output bound process and CPU bound process. So the same thing we are discussing here. So generally, when you compare input-output process to a CPU bound process, input-output processes are very slow. After each input-output call, CPU has to sit idle until the input-output device completes the operation. And so processor saves the status of the current process, basically, and executes some other process. So when you say saves the current status of the process means now a process is in the running state because of input-output event. Where will it come? For which state it will transition? Tell me somebody. Can somebody quickly tell which state it will transition if an input-output event happens? So process is in the running state. Now an input-output event is happening. So the current process to which state it will transition? Currently a process is running. An input-output event is going to happen. So what is the state this process will transition into? Will it go here, here, or here? Three paths available. Which one will it go? Because of a input-output event. It will go to the block state. See, I explain. I explain here. It comes to the block state. So that's what is mentioned. So after each input-output call, CPU has to sit idle until the input-output device completes the operation. So whatever is running now, the processor will save the status of the current process and execute some other process. So there will be another process that is in the ready state that will come and run. When input-output operation is over, the input-output devices issue an interrupt to CPU, then restores the original process and preserves the execution. That means what happens is from blocked, when this process is in the block state, once the input-output operation which caused it to come to the block state will say, okay, now I have completed. Now the current blocked one can start running again. So to start running again, what will happen? It will go back to ready state, and from ready again, it will come to running. Right? That's how you have to understand this flow, how it works. Okay, that's all for today. So I just want to know you understood this transition, how they are working, and things like that. I just want to clarify, because this is the important discussion of the whole section we discussed today. Do you understand Did you understood? Clear. Cool. Right. So I hope that should be a good thing. It's a very easy area to score marks. Let's see in the next lecture. We'll finish the chapter and then do some questions on this. In the meantime, you can search past paper questions on this and attempt this. Basically, there are many questions. It's very easy. You can try that out. Okay, so let me conclude it for today. There are no questions. You can continue in the next class.